Hello everyone, today we will be covering the learning of objective 2, which is to understand the energy changes in a system. So in this session, we will be covering the ways in which energy is stored before and after any changes. Then calculation of the changes in energy involved when a system is changed by heating or work done by forces or work done when there is a current flow. And finally, calculating the amount of energy associated with a moving object, a stretched spring, and an object raised above ground level. So the first one is to explain the ways energy is stored before and after any changes. So let us consider an example. So when an object is projected upwards, so when an object is thrown upwards or when it is projected upwards, so before change, the object possesses kinetic energy due to its initial velocity due to the upward thrust, and it has potential energy due to its height above the ground. So the potential energy is because of the distance from the ground, and kinetic energy is due to its initial velocity. And after change, as the object moves upwards against the gravity, the kinetic energy decreases because of the atmospheric friction and then its speed decreases. So due to that, the kinetic energy decreases. And at its highest point, its kinetic energy is momentarily zero. So it is in fact momentarily zero, beyond which it starts falling, while its potential energy, which is the energy measured from the ground to the height at which the object is placed. So at that point, your kinetic energy is zero and its potential energy is at its maximum. So during descent, the potential energy decreases because of the decrease in height, and then kinetic energy increases because of its increasing velocity and due to the force due to gravity. So next example we look into a moving object hitting an obstacle. So before change, the moving object has kinetic energy due to its velocity. So an object is moving, it has kinetic energy. But after change, upon collision, some of the kinetic energy is transferred to the obstacle or converted into other forms of energy, which is like sound or heat. So when you hear a collision, so there is always a noise and there is always some heat generated. So it is so that conversion of energy takes place. Then the object's velocity may decrease or become zero, leading to a decrease in kinetic energy due to that collision. Then an object accelerated by a constant force. So before change, initially the object has potential energy and possibly kinetic energy if it is moving. So it also has energy with its position in a field like gravitational or electric potential energy. So the object is accelerated due to its kinetic energy and also other forms of energy like gravitational or electric potential energy. But after change, as the constant force accelerates the object, its potential its potential energy might decrease if it is moving downwards or increase if it is moving upwards. So after change, for example, if you throw a ball up and then it hits the ground, then it goes up, it rebounds. So that time its kinetic energy increases. So this increases due to a change in velocity, and the energy input from the applied force can lead to changes in potential and kinetic energy. So that is how there is changes in the energy before and after change. And then a vehicle slowing down. So in this, before change, the moving vehicle has kinetic energy due to its speed. So a vehicle which is moving, it has kinetic energy because of its speed. And after change, when brakes are applied, so some of that energy, it gets converted into other forms like heat energy, which is due to the friction of the road and friction in the braking system. And subsequently, there is a decrease in the kinetic energy due to the decrease in speed of the vehicle. So these are few examples where there are changes in before, where we have seen the changes in forms of energy before change and after change. And now the next example is bringing an object to a halt. So before the change, the object has kinetic energy due to its motion. But after change, when the object is brought to a halt, its kinetic energy is completely converted into other forms. So such as heat or sound due to friction or impact. The object's kinetic energy also becomes zero. So that is what happens when you're bringing an object to a halt. So these are few of the examples we discussed, like before the change. So next we look into calculation in the changes in energy involved when a system is changed by heating or work done by forces or work done when there is a flow of current. So in heating, the change in energy due to heating is calculated using the formula change in thermal energy is equal to delta E. Delta represents the change, E represents the form of energy, M is the mass of the substance, C is the specific heat of the specific heat capacity of the substance, it is a constant, and delta T is the change in temperature. So delta E, that is the change in thermal energy, it is measured in terms of joules. Then the mass you have in terms of kilograms, and C is the specific heat capacity of the substance in joules per kg and Celsius, and delta T is the change in temperature, which is in degrees Celsius. So in this, let us look into an example. So if you want to calculate the energy required to heat 1 kg of water, then for example, C is equal to 4186 joules per kg degrees Celsius from 20 degrees to 80 degrees. So change in energy, it is you can use the formula M into C into delta T. So mass of the water is 1 kg. Then you have specific heat is 4186 joules per kg per degree Celsius, and delta T is the change in temperature. So you want to change it from 20 degrees to 80 degrees. So the change in temperature is 80 degrees minus 20 degrees. So delta E is equal to 1 kg into 4186 into 60 degrees Celsius. So upon doing the calculation, we have delta E is equal to 251,160 joules. So it would require approximately 251,160 joules of energy to heat 1 kg of water from 20 degrees to 80 degrees Celsius. So this is an illustration of heating, change in energy due to heating. Then we have work done by forces. So the work done by forces by an object is calculated using the formula W is equal to F into D into cos theta. So W is the work done in joules. Then F is the force applied in newtons. D is the displacement of the object in the direction of the force in meters. and theta is the angle between the force and the direction of displacement in degrees. So now let us look at an example how work done by forces on an object is can be calculated. So for example, if you have 100 Newton force applied at an angle of 30 degrees in the direction of motion, then the object moves 5 meters in that direction. So total work done is equal to 100 newtons into 5 meter into cos 30 degrees, which is approximately, no, not approximately, it is actually 433 joules. So cos 30 degrees is equal to 0.86 as per the tables. So the work done by the force in this case is 433 joules. So next we look into electrical changes. So work done when there is a flow of current. So the work done when a current flows through an electrical circuit can be calculated using the formula W is equal to V into Q, where W is the work done in joules, V is the voltage in volts applied across the circuit, and Q is the charge in coulomb. So all these are standard units of measurement of the different different forms of energy or the different SI units. So work done is measured in joules, voltage is measured in volts, and charge is measured in coulombs. So let us look into an example. So if a circuit has a voltage of 12 volts and a charge of 5 coulombs passing through it, then your work done is equal to 12 volt into 5 coulombs, which is 60 joules. So the work done when 5 coulombs of charge pass through a 12 volt circuit is 60 joules. So this is an example. So next we look into calculation of the amount of energy associated with a moving object, a stretched spring, and an object raised above ground level. So these are the different scenarios for calculation of energy. So the first one is kinetic energy for a moving object. So the formula of kinetic energy, so basically the concept of kinetic energy is that it is the energy a moving body has as a result of its motion. So a body which is not moving does not have any kinetic energy. So so the formula for kinetic energy is equal to Ke is equal to half mv square, where Ke is the kinetic energy in joules, m is the mass of the object, and v is the velocity, which is the speed of the object is in meter per second. So this is the formula for kinetic energy. So we look at an example. So if you have a car with a mass of 1000 kg moving at a speed of 20 meters per second, so the kinetic energy generated by the car or the kinetic energy of the moving object is 200,000 joules, which is calculated as half equal to half into mv square. So it is 0.5 into 1000 kg into 20, 20 into 20 meter square per second square. So the kinetic energy of the moving car is 200,000 joules. So next we look into what is potential energy. So potential energy is the type of energy which is associated with the position or configuration of an object. So it represents the stored energy that an object has due to its position or state. And it has the potential to do work in the future. So potential energy, it can be either gravitational potential energy where an object is raised above the ground level, or it could be elastic potential energy due to a stretched spring. So there are two types of potential energy. One is gravitational potential energy and the other is elastic potential energy. So the first one is gravitational potential energy. So gravitational potential energy is the energy stored in an object based on its height above a reference point, usually the ground, in a gravitational field such as Earth's gravity. So the formula for gravitational potential energy is equal to mass into acceleration due to gravity into height above the reference point. So simple formula is mgh, where GPE is the gravitational potential energy in joules, m is the mass of the object in kilograms, and g is the acceleration due to gravity, which is 9.8 meter per second square on Earth, and h is the height above the reference point in meters. So this is the formula for gravitational potential energy. So for an example for this is, if you have a 10 kg object raised 5 meters above the ground, so your potential energy is 10 kg into 9.81 meter per second square into 5 meters, which is 490.5 joules. So the potential energy of the raised object is 490.5 joules. So using the calculation of mgh. So then we have elastic potential energy, which is the second type of potential energy. So this energy is the energy stored in an elastic or stretchable or compressible object when it is deformed from its equilibrium position. So this can apply to objects like springs, rubber bands, or even compressed gas. So the formula of elastic potential energy is P is equal to half into K into X square, where P is the elastic potential energy, K is the spring constant, which is the measure of the spring's stiffness in Newton per meter, and X is the displacement from the equilibrium position in meters. So this is the formula for elastic potential energy. So if you have a spring with a spring constant of 500 Newton per meter stretched by 0.2 meters, your elastic potential energy is equal to half into K into X square, which is half into 500 Newton per meter into 0.2 meter square. So P elastic is equal to 10 joules. So the elastic potential energy which is stored in the spring is 10 joules. So this is an illustration of an example of elastic potential energy. So now we look into the concept of conservation of energy. So if gravity is the only external force which does work on a body, so we all are standing due to gravity. If there was no gravity, we could shift our heads upside down and there would be no difference. So,
Yeah.
so because of gravity, we are standing still. Because of gravity, the objects are placed the way they are. So if gravity is the only force which does work on a body, then the total energy of the body will remain the same. A principle which is known as conservation of energy. So this includes the sum of potential energy and kinetic energy. So mathematically, the conversion of mechanical energy is expressed as initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. That means there is no energy loss. So whatever is the initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. So energy may get transformed from one form to other, but there is no energy loss. So, so this is again represented in equation form as initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. So, breakdown of the principle, we have initial state. At the beginning of the process or motion, an object may have a certain amount of potential energy due to its position and kinetic energy due to its motion. And in the final state, at the end of the process or motion, the object may have a different potential energy and kinetic energy depending upon its position or speed. So, according to the principle of conservation of energy, when no external forces such as friction or air resistance they do work on a system, the total mechanical energy, which is the sum of kinetic energy and potential energy, remains constant throughout the process. So this is a very big assumption that there is no friction or air resistance. In practical purposes, there is always air resistance and there is always friction which works on a moving body. So next we look into the concept of power. So power is the rate at which work is done. So basically, it is measured in watts. So the formula for power is force into velocity. So where P is the denotation of power, which is measured in watts. F is the force applied, which is measured in newtons. V is the velocity of the object, which is measured in meters per second. So, for example, mechanical power. In the context of mechanics, if you have a force applied to an object and it moves with a certain velocity, you can calculate the power exerted by that force. For instance, when you are lifting a heavy object at a constant speed, you can calculate the force required to lift it. So, if you are lifting a 100 Newton weight with a velocity of 2 meter per second, the power required is 100 Newton into 2 meter per second, which is 200 watts of power. So that is how all the mechanical equipments are graded so that whenever they want to do lifting work, the amount of power, how much is required. So then we have electrical power. So in electrical circuits, power is calculated using the formula power is equal to voltage into current. So this equation relates to power to a voltage across a component and current flowing through it. So if you have a device with a voltage of 112 volts and a current of 5 amperes running through it, the power consumption of the device would be 120 volts into 5 amperes, which is 600 watts. So these specifications you would have seen written on your, say, phone charger, on your electrical sockets, like how much ampere it is, and how much volt is the light bulb or LED bulb. So these specifications are generally written on that. So that is all for today. In case if you have any questions, you can let me know.
Okay, thank you.
Thank you. Thank you for your time.
Pleasure. Thank you.